All right, we are going to talk about RLC circuits and differential equations. I'll walk through what this whole diagram is in a moment, but before I even get started, I should put the disclaimer out there that this is electricity by a math teacher. So I am going to give you my understanding, which is very limited, of electricity in order to show where an equation comes from. And once we get to that equation, then we'll use that equation. And we'll do a bunch of differential equations with it. We'll solve different types of them. All right. So first off, E, energy source. We measure it in volts, V, right? And it's E of T. So what I mean by that is, like, I could plug in a battery if I wanted, then my energy source would be constant, right? Or I could plug something into the wall, and then you get what's called alternating current. It goes up and down, up and down, up and down. We'll talk about that in a little bit too. So right here we have a capacitor. It has its C measures its capacitance, and the units of measurements are farads. So it would, or F, right? We just use F, just like we use M over S per meters per second when we're talking about velocity. I use F for farads when I'm talking about capacitance. Over here, we got a little swirly. It's an inductor. In the letter we use for inductance that says what the inductance of this inductor is L, and it's measured in H, which stands for henries. An inductor is a little, it's usually a rod of some sort with a wire wrapped around it. Down here we have a resistor. We use R, and it measures the resistance in ohms. The most common resistor that you probably are familiar with is the light bulb. Light bulb's just a simple resistor. So I'm going to write the equation, and then I'm going to tell you a couple different parts of it, and then I'm going to show you where it comes from. So the equation that we are going to generate in this video is Li double prime plus Ri prime plus 1 over C times I is equal to E prime of T. Before I do that, I guess I should say what I is. So I, this guy right here, is representative of the current through this circuit. So I can change the current by changing the values of the capacitance, the inductance, the resistance, and the energy that's being applied to the circuit. What's current? Well, it's what it sounds like it is. If you think about a river or a stream, or I guess a river or a stream. I was going to say a lake, but a lake doesn't really have a flow. If you think about a river or a stream, I have water that's flowing through it, right? It has a current. The current is a way to measure how much water is going through. So I is current. And then the other thing that we're going to talk about is Q, which is the charge. Oops. Now, there's some properties of electricity in that if you were to set this thing up with a different capacitor, an inductor, a resistor, and some energy source, and send some current through, then the current at any given time here is the same as the current at any given time here, right? It can change, right? But the current through the whole circuit is always the same. So if I can find I, then I know how fast electricity is flowing through this circuit. Now, Q is the charge, right? So if I were to take the derivative of Q, dQ dt, then that is the time rate of change of the charge. Well, that is, that is the current, right? So I is current, and then Q is charge, and then the time rate of change of the current is, the time rate of change of the charge, Q, is current. That should make some sense. At least maybe sort of half intuitively. If you think about it, oh, I got a little electron, right? Or I got a certain amount of electrons. That's my charge. And then how fast are they moving? At what rate? Well, that is the current, right? So this is how many electrons do we have? in a simple way. And then this is how fast are they moving. So I'm going to write a couple things. Resistor, capacitor, and inductor. So there's like a law out there in electricity that says that each of these things here forces a voltage drop, and that the sum of the voltage drops is going to be equal to the volts that are coming out of this energy source. So the voltage due to a resistor being in a circuit is V equals current times resistance. V equals IR. You can actually make sense of that with straws. That would be like the wire, or that would be like the resistor, and different size straws or different number of straws, and blowing air out of them. You could think about the current as the amount of air that's coming out, and the voltage as the how hard you're pushing air out of your mouth. For example, if I had a tiny coffee stir and I pushed, right, not a lot of air would come out, compared to if I gave the same push with like a soda straw. I'll leave that at that. The next one is the capacitor. The voltage drop due to the capacitor is 1 over C times the charge. I'm not going to talk about that too much or at all, I guess, but that's the way it is, right? Remember, my goal is really just to get to this equation and have you understand a little bit of what's going on. And then we'll just do some math with it. The last one is inductance. So the voltage drop due to inductance is the voltage drop due to an inductor is the inductance times di dt. So the rate of change of the current, because the current can change, right? So I could write that in a more simple form as L times I prime. So what we can do next is what I said earlier, is that the sum of the voltage drops from this and this and this, it's always got to be equal to the energy that's being applied. I can have more complex circuits that would have different rules, but in this simple circuit here, sum of the voltage drops is E of t. So I'm going to write this plus this plus this is equal to E of t. It's sort of what we did with F equals ma and mass times acceleration and some of the forces when we did springs. So what do we get? I'm going to do, acting funny. That one first, and then I'm going to do this one, and this one. I think the battery on my stylus is dying right now, which is very unfortunate. So L I prime plus, and then I'm going to write resistance times I. The reason I switched them for this one is because this is the way you normally see. You see V equals IR, but in our case here, we want to have the R out front. And I think you'll see why in a moment. Plus 1 over C times Q is equal to E of t. So that's because of laws from physics, okay? Laws from the physics of electricity. So now what I can do, remember, we want to get to that equation right here, and you may already see it showing up. I'll zoom out a little bit so you can look at both of them and see if you can see it coming. Maybe you can see it coming. What am I going to do? I'm going to take the derivative with respect to time of this. Remember, or maybe I didn't say this, an inductor has an inductance. A resistor has a resistance. We're not considering capacitors or inductors or resistors for which those values can change. So those are all constants. So I don't have to use product rule or anything. I just write L I double prime plus R is a constant times what's the derivative of I with respect to time? I prime plus 1 over C times Q prime is equal to E prime of t. Now, I want you to take note that dq dt, the time rate of change of Q, is just I. So come down here. Remember, this was the derivative with respect to time, so that is just I. And I get my equation, which is L I double prime plus R I prime plus 1 over C times I is equal to E prime of T. And this is the equation that we're going to use to solve for I of T equals. So that will help me solve for the current in a circuit. And what I want you to notice before I hit stop is that this is a second order linear differential equation with a force being inputted. So this is something that we can solve using all the math that we have learned in this unit. Two examples, one with a battery and one as if it was plugged into the wall.